Well, we have we have calculated the power dissipated in the conductor in the conductor with the length of L. Now we can see that this power is negative, which indicates losses. Okay, on the other hand, we may also simply compute the power loss using the Joule effect, or simply the resistance of the conductor is equal to L over conductivity multiplied by S, where S is equal to PA squared and power loss is equal to I squared multiplied by R and is equal to I squared L sigma PA squared, which is the same result as we get here. Okay, and it demonstrates that the dissipated power in the conductor due to the resistance can be obtained through the power penetrating into the conductor by electromagnetic fields. By the use of the Poynting vector, the power dissipated in the conductor does not enter the conductor through its connections, but through electric and magnetic fields generated by the power source. Okay, by the power source and penetrates through the surface of the conductor. And this shows that unlike the common view of current flowing through the conductor and encountering resistance, the use of Poynting vector indicates that power is propagated by the electric and magnetic fields. In effect, the conductor is not necessary for the propagation of power, but it used to guide the power where it is needed. And the dissipation is a consequence of the conductors not being the ideal. Okay. The next problem. So, first of
Ertak
all,
ishlayapman hozir.
first of all, okay, should I wait or no? Uh, are are you solving? Should I wait or not?
Men qo'yaveramiz ustoz. Zo'ring ustoz baribir xato.
Okay. First of all, the as we can see here, a electric field intensity and magnetic field intensities are given in phasor forms. First of all, we switch to the time domain. So in time domain, electric field intensity ET will be the real part of our phasor. Yes, EP e to the power of j omega t. So where EP is given as like this, E real plus J E imaginary, and e to the power of j omega t is, as we know, cosine omega t plus cosine omega t plus j sine omega t. So we need to compute the real part of this complex number. The real part of this okay. Of this complex number will be the ER multiplied cosine omega t minus EI multiplied sine omega t. So ER multiplied by cosine omega t minus EI multiplied so sine omega t. Similarly, we need to compute the magnetic field intensity in time domain. Magnetic field intensity in time domain is equal to the real part of HP is here HR plus J HI multiplied cosine omega t plus J sine omega t, and the magnetic field intensity HT in time domain will be HR multiplied cosine omega t. Again, HR multiplied cosine omega t. Okay, HR multiplied cosine omega t minus HI multiplied sine omega t. Now we may compute the time-dependent Poynting vector, which is PT is equal to E T cross HT, where ET is ER cosine omega t minus EI sine omega t cross HR cosine omega t minus HI sine omega t. And if we perform the calculations, what we have? ER cross HR cosine square omega t. So ER cross HR cosine square omega t plus let's write sine square omega t as well, EI cross HI sine square omega t minus ER HI sine omega t cosine omega t. Okay. And minus EI HR sine omega t cosine omega t. Okay. Okay. Cosine omega t. And now the time averaged pointing vector is time averaged pointing vector is 1 over t from 0 up to t et cross ht e yeah et cross ht dt. Now what is the period? Period is 2p over omega, and et cross ht we may this integral we may split into 4 integrals. This is the first, this will be inside the first, this will be inside the second, in the third, and in the and the last will be inside the last integral, and let's compute. Okay, I will go to a new page. The first integral will be ER cross HR. So ER cross HR, instead of 1 over T, we put omega over 2P, and integral from 0 up to 2P over omega. And inside the integral, the time-dependent term is only cosine. Cosine squared omega t dt. Plus, inside the second integral will be the second EI cross HI, will be second term, plus EI cross HI omega over 2P, the integral from 0 up to 2P over omega of sine squared omega t dt, plus inside the third integral will be, okay, inside the third integral we may put both of them, because there is a common term inside the both of them, and the common term may go outside of the bracket, and we get plus minus EI cross HR plus ER cross HI omega over 2P, and inside the integral is from 0 of up to 2P over omega. And inside the integral will be sine omega t cosine omega t. Sine omega t multiplied by cosine omega t dt. So for the simplicity, we may take each integral and compute it separately. Let's take the first integral, cosine square omega t dt. Okay. Let's compute first integral from 0 up to 2p over omega. From 0 up to 2p over omega of cosine square omega t dt. It can be computed as, so from 0 up to 2p over omega of 1 over 2 minus yes 1 over 2 minus okay, cosine 2 omega t 2 omega t. So cosine squared minus sine squared plus, sorry, will be plus, okay, 2 omega 2 over 2 dt, and it will be equal to t over 2 plus sine 2 omega t over 2 omega multiplied by 2, 4 omega, where t from 0 up to 2p over omega. If we put, okay, if we put 0, we get 0. If you put 2p over omega here, if we put 2p over omega, 2 and 2 simplifies, omega omega simplifies, and remains only sine of p, which is again 0, and remains only 2p over omega over 2 omega, or p over omega. Okay, the value of the first integral is p over omega. Now let's compute the second integral. So integral of from 0 up to 2p over omega of sine square omega t. Okay. So integral of from 0 up to 2p over omega of sine square omega t dt. So what about this? This will be 1 over 2 minus cosine 2 omega t from 0 up to 2p over omega, 1 over 2 minus cosine 2 omega 2 cosine 2 omega t over 2. So cosine plus sine minus cosine plus sine, yes, and it will be equal to the integral will be equal to t over 2 minus sine 2 omega t over 4 omega from 0 up to 2p over omega. Again, if we put instead of t 0, everything will be 0, and if we put 2p over omega, if we put 2p over omega, this will be also again 0, and again we have the value of this integral will be 2p over 2 omega or p over omega, p over omega. Okay, the value of the second integral is also p over omega. Well, what about the third integral? What about this integral? Let's compute the third integral sine omega t cosine omega t. Integral from 0 up to 2p over omega sine omega t multiplied cosine omega t of the t. This will be sine omega t multiplied cosine omega t will be okay 1 over 2 sine 2 omega t or sine 2 omega t over 2 from 0 up to 2p over omega. If we integrate it, the integration of from sine okay, the integration from sine should be cosine minus cosine minus cosine 2 omega t over 2 not 2 4 omega, and it changes from 0 up to 2p over omega. Okay, if we put 2p over omega, so omega simplifies, 2 simplifies, we get minus 1. If we put 0, we get 1. Okay. No. No, we should get as a result of this integral, we should get 0. Where did we do a mistake? So sine omega t multiplied by cosine omega t Okay. Okay, the result of this integral should be 0. I will review this example later. So the result of this integral must be 0, and if we go back to our to our equation, here we have 0, and okay, as a result of p averaged or pointing vector time averaged, we get so let's look at the first term, er cross hr multiplied omega over 2p multiplied p over omega. So omega and omega simplifies, p and p simplifies, we get there remains only 1 over 2, or er cross hr over 2 plus, here again omega omega simplifies, pp simplifies, ei cross hi over 2. Okay, and the resultant time averaged pointing vector will be, so it is simple, er hr plus ei cross hi over 2. So we have found the time averaged pointing vector of our problem. Okay, try to compute the second part of the question by yourself, and tomorrow we will discuss the second part of the problem. But try to evaluate by yourself first at home. So see you tomorrow.